So here on Talk the Thought Process, we're going to work on stoichiometry. This is where we use a balanced chemical equation in order to solve problems. It's like using a recipe to, follow how we cook something. And we can use that recipe to determine how much of something we need or how much of something we expect. The same is true in chemistry when we have a balanced chemical equation. So here's an example of a four-part problem involving stoichiometry. And we can just glance at the questions to see we're going to be asked to calculate how many grams or how many moles or what mass are we going to get. And so whenever we do this sort of problem where we're calculating how much or how many, the first thing we need to do is to balance our equation. So we've got an equation here. We've got ammonia, a gas, copper 2 oxide, a solid, reacting to form copper, a solid, nitrogen, a gas, and water, a gas. And so the first thing I want to do is make sure that we have a balanced equation so that we can use it to solve some problems. So I see here, first of all, that the nitrogens are not balanced. We have 1 on the left and 2 on the right. So I'm going to use my intuition to put a 2 here front of that nitrogen in the ammonia, and then see if I can balance everything else. Right, so now I've got 2 times 3 is 6 hydrogens, so I'm going to put a 3 in front of this water over here. See how that looks. 3. And then that shows me now that I have 3 oxygens. I need to put a 3 over here as well. And now that I have 3 coppers, it looks like I need a 3 over here. This is called balancing by inspection, where you just kind of look at the reaction and you add stoichiometric coefficients, these are these numbers in front, to make sure you have the same amount of atoms of each type on each side of that arrow. So let's just check that again. We have 2 nitrogens here. We have 2 nitrogens here. We have 2 times 3 is 6 hydrogens here. We have 3 times 2, 6 hydrogens here. We have 3 coppers. And we have 3 coppers, and we have 3 oxygen, and here we have 3 oxygen. Okay, so now that we have the balanced equation, we can use it to solve problems. And we're going to start simply with the first one and go one step at a time. But before we do that, the other thing that I like to do when I have stoichiometry is I like to make a note of the molar masses of the various elements that we have, because those are needed when we do stoichiometric calculations. And for that, we're going to need our periodic table. And so, for example, our first compound in here is ammonia. It's nitrogen, which has a atomic mass of about 14, and then there are 3 hydrogen atoms attached, each which has an atomic mass of 1. So the molar mass of NH3, ammonia, is 14 plus 1 plus 1 plus 1 is about 17. So what I like to do in my problem is to just make note of that up here, that for ammonia, there's 17 grams per mole of ammonia. And I'm going to do that for each of my things in my reaction. So I have copper oxide. Now I know oxygen is 16 because I use that a lot. I don't use copper quite as much. So I'm going to look closely here. Copper is 63.5. So I'm going to have 63.5 plus 16. 63.5 plus 16 is about 79.5 grams per mole. Copper again is 63.5 grams per mole. Nitrogen, and now remember, is 14, and there are 2 of them here, so nitrogen is 28 grams per mole. And hydrogen, which maybe by now you've used a lot, you'll know for water that oxygen being 16, 2 hydrogens, 1 gram each, this is 18 grams per mole. Right, so everything we need to know to solve our problems are in this balanced equation. We need the stoichiometric coefficients, which tell us the ratio in which all these different things react. And if we're going to be converting from grams to moles or moles to grams, which we often do, we're going to need these values here, the mass per mole for each of these species. And of course, we find those from the periodic table. Okay, so then if we go to our first problem here, how many grams of CuO is required for 28.2 grams of ammonia to react completely? So let me just make a new page for that. Okay, so again, when I do these problems, what I like to do is start on the left with what we're given in the problem, right? It's asking for how many grams of CuO, and it's giving us some information, 28.2 grams of ammonia. So that's always what I'm going to start with. So I put that over here, 28.2 grams of ammonia. And I'm going to be multiplying this by a whole bunch of conversion factors. And at the end of the day, I want to have an answer in what it is they're asking me for. Asking me for how many grams of copper oxide. So over here, I'm going to have grams of copper oxide. And then all the conversion factors that I get are going to come from my equation and also from those molar masses that I just put up. So again, ammonia, it's 17 grams per mole. And what was copper oxide again? It's not one I use every day. 79.5 grams per mole. So we'll put that one up here. 79.5 grams per mole. Okay, so remember to sort of visualize what's happening in the problem. We're going to be having 28.2 grams of ammonia. We want to know how much of the copper oxide is needed to react with all of that ammonia, right? To use it all up to form the products. So we're going to use our recipe for the reaction, which is the balanced chemical equation. And we can't use that recipe unless we convert things to moles, because these numbers in front are all in moles and we need to work in moles. So first we convert our grams of ammonia to moles of ammonia. And we should know how to do that by putting our grams of ammonia on the bottom and the equivalent number of moles on the top. Right, and 1 mole of ammonia has a mass of 17 grams. So we already have that up there. Right, so we're getting this set up so that our grams of ammonia are going to cancel out, and we'll then have moles of ammonia. And in our question here, we want to know how much copper oxide. So we're going to first see how much copper oxide reacts with our moles of ammonia. Right, so we want moles of copper oxide on the top, copper 2 oxide, and then we want our moles of ammonia on the bottom. Right, because copper oxide is what we're looking for. Ammonia we want to go away, right? So we put that on the bottom to cancel out with this. And we have to look to our equation to see what numbers we put in front here. So from here we see that 2 moles of ammonia, 2, are needed to react with 3 moles of copper oxide, 3. Right, so that comes from the stoichiometric coefficients. So then we'll have our moles of ammonia, which have canceled. We have moles of copper oxide, but we want to know our grams of copper oxide, so we have to do one more conversion here. So we'll put moles of copper oxide on the bottom, 1 mole, and then we see here there are 79.5 grams of copper oxide, copper 2 oxide, in 1 mole. Right, so our moles will cancel there, and we'll end up with grams of copper oxide. Right, so all of the problems are the same and all of them are different, right? So they use the same conceptual framework, that we have a recipe for the reaction. We can start with what we're given, and we can end up with what we want by converting one step at a time. And the important thing is to know where these conversion factors come from, right? So from mass to moles, we need the molar mass, the mass in 1 mole. From moles of ammonia to moles of copper 2 oxide, we need the stoichiometric coefficients. They react in a ratio of 2 to 3, 2 in front of the ammonia, 3 in front of the copper. And then to get back from moles of copper to grams again, we have to use the molar mass, 79.5. Right, and so we've got the problem hopefully set up correctly. And then we have to make sure we use our calculator correctly. So I'm going to give it a try and type it in. 28.2 times 1 times 3 times 79.5. Then we divide by all the numbers that are in the denominators, divided by 17, divided by 2, and divided by 1. And so what I get is 197.8 grams. We'll try to follow our rules for significant figures. Since we have 3 significant figures in the data given, we want 3 significant figures in the answer that we get. So this is going to be 198 grams of copper oxide. Right, so the important thing, again, is to make sure we understand where we got all the conversion factors that we used. Okay, so now we can go on to the next problem. How many moles of N2 would be produced from that reaction? Okay, so we've got part of it started for us, right? Except that in this case, we're interested in the moles of N2. We're not interested in the moles of CuO. So again, we can do what we did before. We'll start with what we're given, right? What were we given in the problem? 28.2 grams of ammonia. So we'll start with that again. 28.2 grams of ammonia. That's what we're starting with. And now we have a different desire here. We want to find out moles of N2. Right, so we want to know, if we start with 28.2 grams of ammonia, how many moles of N2 will we end up with? We use our same thought process, right? So we're going to start here by converting grams to moles because we need to do that to use our equation. And I happen to remember that the molar mass is 17. We could look back if we forgot, but there are 17 grams of ammonia in 1 mole of ammonia. We don't want to know the moles of ammonia, though. We want to know the moles of N2. So we have to look at the ratio in which they react. So we're going to put the moles of ammonia on the bottom because they cancel out, and the moles of N2 on the top. What number goes in front of here? Well, we've got our balanced equation. If we didn't have our balanced equation, it would be a hard thing to do. But we know that for every 2 moles of ammonia, we produce 1 mole of N2. So those are the numbers that go there. And I think that's all that we need because we're converting grams of ammonia to moles of ammonia, and we want to have moles of nitrogen. So let's see what we get for that one. We have 28.2 divided by 17 divided by 2 equals 0.829. I have 0.829 moles of ammonia. Okay, so we've done 2 of our 4 problems, and so we're going to pause here and come back in a moment to finish this up.